इसका माइक नहीं है, ये डायरेक्ट रिसीवर है.
Director is not coming.
We have actually two parallel functions happening. One function in Delhi. What happened was we scheduled this event, sent out invites to confirm, and then the Delhi event happened. I had cancelled this, guests confirm, many others confirm, directors confirm. That is the one. Yeah, that is the one. Very good. We have टेक्नॉलॉजीला हे घेऊ का तर मला ते म्हणले नको नको काय मला ते म्हणलं को ऐकू आलं
त्याच्यातून खराब झालं कॅमेरा अपलोड होतो.
ऑगस्ट सप्टेंबर वरचं कवर लाईव्ह
स्वागत है, वंदन है, अभिनंदन।
CSIR lab is having 1 TPD plant already. And from this 1.5 tons per day pilot plant of CSIR, we will get syngas. And from the syngas is getting converted into methanol, wherein CSIR itself can address 50 kg per day. So the remaining syngas will be addressed by another constituent laboratory, which is CSIR-IIP, and they will be using the water gas shift reaction, and they will be converting syngas into methanol. So in the entire history of CSIR, this is the first time we are going to have two pilot plants, meaning is one pilot plant of CSIR and the another pilot plant of IIP. Both are going to be located in the campus of CSIR, and therefore this is a new, I would say, new initiative and a very positive initiative, so that the entire coal to syngas and the syngas is getting converted into methanol. Now, taking cue from methanol, it is now NCL who will be converting this syngas into DME. And this DME conversion, that is especially from methanol to DME conversion, NCL is going to work with IOCL. And parallelly, another laboratory, for example, even CSIR IIP, they have plans to work with NTPC again to methanol to DME. And similarly, IICT is also coming up with a proposal that methanol to DME, they'll be joining hands with BHEL. Therefore, if you just start from coal to reach this DME, number of labs are involved in this, and number of technologies are also could be found in this particular value chain. So this is the amazing journey of coal to hydrogen and syngas and methanol and methane. And if you just talk about this hydrogen, of course, before even the country announced this national hydrogen mission, it was only CSIR who announced this CSIR's hydrogen mission way back 3 years back itself, and we are now completing the first phase of CSIR's hydrogen mission. And yes, without any hesitation, we'll be moving ahead with the second phase of CSIR Green Hydrogen Mission, because Green Hydrogen Mission is again a great success as far as CSIR is concerned. So under Green Hydrogen Mission, again, we have three important components: hydrogen generation, hydrogen utilization, and hydrogen storage. So in the case of hydrogen generation, again, we have two types of electrolyzer, whether it is PEM electrolyzer or alkaline electrolyzer. So we have labs like CSIR, Central Electrochemical Research Institute, National Chemical Laboratory, NCL. So both the labs are working with respect to the development of electrolyzer. And when it comes to, again, fuel cells, whether it is any kind of a fuel cell, I would say, whether it is an open type or a closed cathode, so they also gain high temperature, low temperature fuel cells. It is only these two laboratories like CSIR and NCL. Both the labs are working together for about 2 decades, for more than 2 decades, I would say. And we have already created some success stories, and we are coming up with many more success stories in the coming days also with respect to fuel cell. Because this fuel cell technology, once we just gifted it to the then Vice President of the country and the President of the country, a fuel cell stack in one of the foundation days. And later we proved that fuel cell driven car, it was demonstrated, maybe on a road show. Similarly, fuel cell powered bus. Now, recently, our Honorable Prime Minister, he traveled in the water vessel. So there also it was powered by CSIR's technology, which is a fuel cell powered water vessel. Therefore, this is again a proven, demonstrated technology of CSIR. Now coming to hydrogen again, when you talk about this hydrogen storage, so till date, countries depending upon other countries for storage cylinders, days are not so far off. Our CSIR's energy theme driven storage technologies will definitely help the country in a major way. We'll come up with the type 3 and type 4 cylinders also. And the very interesting point is, even for this type 4 cylinder making, right now we are using Torre carbon. And again, days are not so far off. We'll be using our own NAL's technology-driven carbon fibers, by means of which CSIR CMERI, who is now developing the type 4 cylinders, they'll be using NAL's technology. Therefore, NAL and CMERI putting together, we'll be coming up with the end-to-end indigenized type 4 cylinders for hydrogen storage. And that is the success story that I'm really awaiting to look for. And when I was just talking about this alternate fuel and alternate energy, then I made a mention about storage. So when it comes to storage, there are different types of storage. One is hydrogen storage, which we talked about. So the other one is the storage of renewable energy. So this is where batteries are taking a major role. So we are all aware that this ISNGES is another big flagship event, and we have 1,000 batteries producing facility in our Chennai center, CSIR-NCL Chennai center, which is again a part of a success story of energy team only. So this is where batteries as energy storage devices, we have proven it with respect to lithium batteries. Now in phase 2, we'll be moving towards the sodium-ion batteries. Already NCL is also working to some extent in the case of sodium-ion batteries, and CSIR-NCL has come up with success stories with respect to protecting the cathodes, anodes, electrolytes, everything with Indian patent. So we have complete IP protected indigenous cathode, anode, electrolyte, and even processing technology also as far as sodium-ion battery technology is concerned. Therefore, the success story on sodium-ion battery, that also is going to happen maybe in another 1 or 2 days through this energy team. And of course, we are always getting ready with respect to the futuristic options. So that is where the redox flow batteries are also finding a place. So CSIR-NCL is working with a big deal on redox flow batteries. I wish to hear success stories related to redox flow batteries also, and I look forward success stories from that area in the coming days. Now coming to the other storage, even cavern storage also, I should appreciate Dr. Lele is working closely with the other team directors from CIE team, that is the Civil and Infrastructure team also. So labs like ACRC, CBRI and NGRI will also be working along with the energy team related laboratories, and we'll come up with some technological options with respect to cavern storage. And when we are talking about this CCUS, carbon capture, utilization and storage, I think we have to prioritize this kind of a cavern storage also. So whether it is hydrogen storage or chemical into electrochemical energy, is storing this energy in the form of electrochemical energy or cavern storage, again it is the energy team which is going to give the technology related solutions. Therefore, in one line, I would say when the country is concentrating on different securities, the energy security related all possible technological options are being practiced. In some cases, we have demonstrated, and in some cases, we will demonstrate in the coming days with a completely indigenized technology packages. So, taking this occasion, I wish to congratulate Dr. Ashish Lele for his dynamic leadership, not only as a lab director of NCL, but also the team director of E2D team. He is taking this team to a entirely different route and the indigenized route. And I should congratulate all the participating laboratories also on this particular occasion, because now we are entering into the new era of 1 week, 1 team. Last year, we successfully completed 1 week, 1 lab. So each lab, we were celebrating our success through our laboratory-driven success stories. Now, this is the time that we have to showcase to the entire nation and to the globe that we as a team, we as a community, we as a thematic consortia, we can still come up with a number of newer success stories, especially because this mob psychology is good for science also, because when we work as a team, then the success stories, they will not pose much challenges and many more challenges, and we will also not require more time to resolve and address such challenges. Therefore, this is a time wherein the entire CSIR family, we will be showcasing that as a team and as a team, we will be coming up with a number of success stories in the coming days. But already whatever we have done as a team and as a team, now we will be showcasing, demonstrating, we'll be explaining, and we'll be brainstorming. We will be making it as an outreach activity also, so that whether it is a research scholar, whether it is I would say social researcher, or a company or an industry or MSME or a startup or an entrepreneur or a self-help group, or whether it is a ministry, line ministry, or whether it is a PSU, CPSC. So whichever way the society or the countries I would say, end requirement, the end user is really looking for some kind of a technology, we may be able to meet out their requirements by way of showcasing and demonstrating the success as well as the matured technologies which are available as on date. And using the same platform of 1 week, 1 team, we can also listen to their requirements and we can rise to the occasion, we can repurpose, we can reorient, and we can redirect our research, the direction of research, the purpose of research, the objective of the research, so that we will be able to fulfill their requirements and we can always stand and we can sustain our role as an all-time relevant organization in the name of CSIR. So I wish this 1 week, 1 theme event of CSIR-NCL's energy theme driven campaign every success. And one more time, because I'm not tired of congratulating energy team, especially for its every leadership and every participant also. Thank you so very much. One more time, good luck to each and every one of you. Namaskar.
हमारी परम माननीय डीजी मैडम का बहुत बहुत आभार है और निश्चित रूप से उनके मूल्यवान संदेश से आप सभी लाभान्वित हुए होंगे। एक बार डीजी मैडम के सम्मान में जोरदार तालियां। बहुत बहुत धन्यवाद। तत्पश्चात आपकी जोरदार तालियों के बीच मैं सादर आमंत्रित करना चाहूँगी हमारे माननीय निदेशक माननीय डॉक्टर लेले सर को कि वे 1 वीक 1 थीम ईईडी कार्यक्रम की संक्षिप्त प्रस्तावना प्रस्तुत करें।
Right, sorry for that bit of a technical glitch. Good morning to all of you. I'm so very happy to see this hall full of people who are bringing new energy into this energy theme. I'm going to be here for about 10-15 minutes just to give you a glimpse of all the activities that are happening in the CSIR lab. There are so many labs where a lot of work is happening under the energy theme that it will be impossible for anybody to present everything that is happening in all the labs in 15 minutes. So all I want to do here is to give you a very short glimpse of a few things. I will not be able to cover everything that is happening in all the labs, and I don't need to, because there is a big exhibition outside, as you must have seen, and a lot more details are available in the exhibition, in the posters, in the prototypes that are shown outside. And they are manned by the experts who have done all that work. So you will get much more details by talking to all those people. So my job here is to just give you a very, very brief overview of what CSIR is doing in this theme. As Dr. Kalai Selvi said, this program is basically an outreach program. We want to reach out to all our stakeholders to tell them what we are doing. and more importantly to invite them to become partner with us so that we can go along this very difficult journey of de-risking technologies, a difficult journey of indigenizing many of the technologies so that whatever is deployed in India is suitable for India, tested in India, and also de-risked in India. So that is the whole point of having these 1 week programs. This particular program is, as DG said, a thematic program. It focuses on the energy theme. There are 7 other themes, and such programs will happen throughout the year in various labs on each of those 7 themes. So in the energy theme, there are, I think, 25 odd labs of CSIR working in this program, and in your kit, if you've got it, there is a calendar of events which labs are hosting which programs on what dates and what is the venue for that. So if any of you, other than being in Pune, happen to be in any of those cities on those days, feel free to go to those labs to see what all is happening in more details in those labs as well. So these are all the labs of CSIR which are working in the energy and energy devices team. And Dr. Ashish Lele, I am the director of NCL, but also the team director of this particular team. So this is basically what we are doing. We have 5 verticals in the energy team. Hydrogen is of course coming in a big way in India. We've been in hydrogen technologies for a very large number of years. Same with batteries. We started the batteries program very many years ago, and we are now looking at next generation batteries. Same with biofuels. We've been working in many types of biofuels for a very long period of time. Something little newer is on the building integrated photovoltaics, onshore, offshore, wind and solar energy storage, and many of those typically non-silicon applications of photovoltaics. So that's relatively new compared to the others, but of course has been around for several years. And then finally the coal-based gasification. Now, the choice of these technologies is very obvious. As India plans to move to a $5 trillion, $6 trillion economy by the end of this decade, and going on to a $30-35 trillion economy by the end of the Amrit Kal, all of these energy vectors are going to be critical for India, okay, for many reasons. And therefore, having noticed these trends, foreseeing these trends up early, CSIR takes the pride of saying that we are one of the earliest organizations to get started to work on all of these energy vectors and develop programs that are not just in the laboratory but translate them to TRL 4, 5, sometimes 6, and then with the partnership of industry scale them up and take them closer and closer to commercialization. So this has been the focus of CSIR Labs. The lab to market program, the lab to market, it's a mission for us, for CSIR, and therefore it's not just publishing papers or filing patents, but also taking the pain, the risks to take the technologies across the TRL ladder, which is a difficult job to do, but is something that we do very passionately. So I'll start with very quickly some of them. This is the battery technology area. As DG said, there is a wonderful pilot plant that is set up at SECRI. The director of SECRI is here with us today. And he has his lab has multiple posters there. It's one of a kind pilot plant in India. There are not many like this in India. And you can produce, the target is to look at 100 gigawatts hours of battery production, 1,000 batteries per day, multiple formats. And as I said, these are technologies that are now going to TRL 6, 7. The USP here is indigenizing the materials, indigenizing new and novel electrode materials, electrolyte materials, and putting all that together into real battery formats which are then tested and globally benchmarked. So this is the pilot plant that does it, and there are very strong collaborations for this work with multiple industries who then take this to the next level of scale up in terms of number of cells produced per day, and also further scale up of prototyping these cells into, converting them into a battery pack, and then putting that battery pack into the drivetrain of a vehicle and actually showcasing some of the prototypes. So this is a very active program. now looking also at the next generation batteries, particularly non-lithium batteries, as well as the solid state, purely solid state batteries. So those of you, if you happen to be in the Chennai center of SECRI, this is a plant that is absolutely worth going and looking at. The next vertical, as I said, is hydrogen, and we've been in this area for a very, very long time. We started from very small cells and have gone all the way to several tens of kilowatt. This stack, for example, is a 20 kilowatt stack, and 2 of these stacks have been put up on a bus. Unfortunately, the video doesn't seem to play, but there's the first fully indigenous fuel cell bus that was developed by our industry partner, who licensed the technologies from us. Beyond that, this is a program where we have looked at many different types of electrolyzers, as well as using hydrogen as a reductant in multiple industries. One of them is to develop the first pilot plant for hydrogen plasma based steel reduction. I don't have to tell you why hydrogen is important. India has a huge national green hydrogen mission. CSIR is very proud to say that we were deeply involved with the line ministry, which is MNRE, to actually formulate, to create the National Green Hydrogen Mission document for India, and we're still working very closely with them to do multiple things. By the way, since you are all here, I take this opportunity to say that the second International Conference on Green Hydrogen is coming up on the 10th to 12th of September this year. Some of you may remember that we had a very large conference in Vigyan Bhavan last year. This one is going to be even larger, and it is going to be in a better venue, which is Bharat Mandapam. So please block your calendar for that. Very briefly about the hydrogen program in CSIR. We are looking at electrolysis as the main technology. We are looking at all 3 types of electrolyzers. You will notice that we are not doing alkaline because that's a very mature technology. There are many doyens of Indian industry sitting here who have very large alkaline electrolyzer plants. So what we have been looking at are more of solid state, solid oxide electrolysis, PEM electrolysis, and anion exchange membrane electrolysis, because these are sort of the new kids on the block. We are also actively looking at seawater, direct seawater electrolysis. Now when we say electrolysis, it's not just the electrolyzer, but all the core technologies that go in making the electrolyzer, whether it's the membranes, whether it is the catalyst, whether it's the bipolar plates. That is the core technology, and that is where we spent a lot of time, not just developing these technologies, but also finding vendors and licensing these technologies to vendors who will eventually manufacture them in India, so that the whole ecosystem for the core technologies is also set up in India. We also look at other new technologies like pyrolysis of methane or biohydrogen. Going to the next value chain, storage and distribution, the focus is on compressed hydrogen gas, and Dr. Kalai Selvi talked about this particular bit. And again, as she said, end-to-end, from carbon fibers to the epoxy resins, to filament winding, to all the valves, sensors that go into the cylinder. So it's a full technology package, and also developing vendors who will do this. Little low TRL level, but upcoming technologies are metal hydrides and the liquid organic hydrogen carrier. So there's a lot of active work happening in these areas as well. The third part of the value chain of hydrogen is the utilization, and again here we've been looking at transportation sector for a long time. I talked about the bus, and Dr. Kalai Selvi mentioned the recent launch of a catamaran, again the first indigenously built catamaran based on the technologies licensed from CSIR. So we've been at it for a long time. And just like electrolyzers, we have looked at every component of the drivetrain also. We have earlier looked at stationary applications of hydrogen in things like DG sets and so on. And more recently, we are looking at various green steel production methods where hydrogen comes in as one of the reductants, not entirely the only reductant, but one of the reductants that go in making steel. So this is a large program for CSIR. It's a 75 crore phase 1 program. It's a funnel-like program where we do a lot of blue sky research, which then with good, well-defined stage gates, we filter some of those programs all the way into the stem of the funnel, which is the mission mode programs. there is a more detailed poster on the SOEC technology. I will not talk about it. Jayanta is here from CGCRI and he will also talk in the technical session 1 to tell you more details about the SOEC technology. We are very, very excited about this technology, and I believe for applications where you need 24/7 hydrogen utilization, this is one of those very, very exciting technologies that India should definitely look at. So more from Jayanta in the technical session 1. I mentioned about pyrolysis and biohydrogen. Again, a very interesting route to pyrolyze methane. This is very exciting because the energy required to split methane is actually lower than the energy required to split water. And we are putting a lot of time and effort in water splitting and not looking so much at methane splitting. Right? It has its own share of difficulties, and that's why we are into it, and we'd like to see what are the best possible solutions to do methane pyrolysis to get not only green hydrogen, especially if you start with biogas, but also to make very high quality carbon, which can then be valorized in many applications such as batteries and fuel cells and so many other things. We are also looking at a full integrated biorefinery to make biohydrogen by dark fermentation, and this is a pilot plant that is already running at IICT. So if you happen to be in Hyderabad, please do visit IICT to see this very nice platform where you can see an end-to-end biomass to not just hydrogen but also manure that comes out, CO2 capture and utilization. So it's a full integrated biorefinery with detailed life cycle analysis worked out. A very exciting development here. This is again, we have some posters on the type 4 compressed hydrogen cylinders. Some of you may have read that just recently PESO approved the first type 4 cylinder just a few days ago. So we are also into this, and two new things that we are doing is our National Aeronautic Lab, NAL, will be bringing its type 7 carbon fibers. But also interestingly, we are looking at a new epoxy resin which is fully recyclable. So at the end of 15 years of the life of the tank, you don't need to throw it, you don't need to landfill it, you don't need to burn it. What you can actually do is to dissolve the tank because the epoxy resin is designed to do that, and you can recover the very valuable carbon fibers and do a new life to those carbon fibers, and therefore the cost of the cylinder on a life basis starts coming down. Similarly, we are developing all these small balance of cylinder components, the valve, the manifolds, some very interesting fiber optic sensors that will control, that will show you real time the amount of stress that is inbuilt into the cylinders as you start using it. Going to the third vertical, which is sustainable aviation fuel, and a huge amount of activity happening here. This is the biofuel. In that, SAF is one of the key things that we are doing. Our lab at Dehradun, IIP, is deeply involved in it. They have pilot plants, they have scaled up those technologies to commercial levels. So we are producing SAF, and this is going to be very important for India because we are signatory to this act called CORSIA, which after 2028 will be mandatory for India to introduce sustainable aviation fuel in civil aviation. And therefore the SAF that is produced by a very unique technology at IIP, details are there outside in the poster, has already been tested with our armed air force as well as in commercial jetliners. So this has already been tested. We are also very proud to say that last year in the 26th January fly past after the morning program, those crafts were flown by IIP's sustainable aviation fuel. In the biofuels area, we are also looking at biodiesel and the compressed biogas also converted into piped natural gas. So we have again a very unique technology to make biodiesel at room temperature. Several plants at pilot scales have been set up. This is a way to decentralize the production of biodiesel, make it where you want to use it. So you don't have to worry about all the issues related to supply chain. On the CBG side at IICT, we have a very wonderful series of technologies, patented, very novel, that look at AGR, the anaerobic gas lift reactor, and also the next generation of it, which can actually convert biomass to give you more than 90% methane. This is very unique because normally you get a 60-40 mixture, 60% methane, 40% CO2. With this technology, you can get in excess of 90% methane. So the metabolic pathways of the organisms have been modified in such a way that you get more methane and less of CO2. These plants have also been set up commercially. There are 31 plants already working, anywhere between 250 kg per day to 10 tons per day capacity. Taking that kind of biogas further, you can separate the CO2 from it and make it fuel grade, transportation fuel grade biogas. And the technology required for that is pressure swing adsorption, particularly the vacuum pressure swing adsorption. This is a technology again fully developed by IIP, and so you can take biogas and make purified fuel grade methane out of it. Again, this is a technology that has already been commercialized. Coming to the fourth vertical, which is solar and wind, and particularly focused on, as I said, non-silicon based solar and new applications of solar. And one of those very interesting application is what is called APV, agro-photovoltaics. And the novelty in what we are doing here is that if you were to have solar farms put up on fields, of course you can imagine that the solar panels will cast a shadow on the plant, and plants need photons to do photosynthesis. So you can't have shadows coming on the farms. And therefore, when you have agro-photovoltaics and you have the conventional technology, your farm yield comes down because the plants don't receive enough photons for photosynthesis. However, what the NIST team here at Trivandrum has done, and again they have a wonderful stall here, please go visit them. They've done some wonderful, very novel optics that make sure that the plants that are on the ground get uniform radiation. This is the novel NIST technology compared to the conventional technology where you will see the shades, right? Which you don't want because that will reduce the farm yield. This with these interesting optics that they have put coupled with the solar panels can give you better farm yields as well as capturing part of the photons into photovoltaics and generating electricity out of it. This is again something very important for India because as we all know, India is an agrarian society. There is a huge amount of agriculture as an industry that happens in India, and therefore our farmers and our agricultural produce should not be affected by putting solar coupled with our farms. The third one is building integrated photovoltaics, again at NIST Trivandrum, and this is a very unique technology where incident, the stray lights such as the light available in this room, which is an indirect light, can also be captured and made use of. So you can improve the energy efficiency of buildings, make buildings more greener, and this requires some really high-end science where what the team has done is not only develop the materials but also completely the full technology package of converting them into inks, formulations, processes for coating them, testing them, integrating them with windows and so on and so forth. So a very, very nice piece of work. Again, the stall is available here for those of you who might be interested in getting more details. The NIST team is here to tell you. On the solar side, our National Physical Laboratory in Delhi is a premier lab that develops all these standard facilities for measurements, monitoring and certification. So they are now putting up a primary standard facility for solar cell evaluation. This is going to be important for India because so far we have been importing solar cells, right, and using them as such. Now the first few plants of actually manufacturing polysilicon solar cells will be happening in India. I know 2 of them are already in the commissioning phases, and therefore the cells produced in India will have to be tested and certified. And this is the only lab in India that is set up to do this kind of work. They've also been looking at flexible photovoltaics. So these are some of the flexible printed perovskite solar cells. Of course, the efficiencies will always be much lower than the silicon cell efficiencies as of now, but there is a lot of work happening to improve the efficiencies. And this is a whole new different set of applications for flexible printed solar cells. Not the same as the standard silicon cells, a completely different set of applications. And further down, we are also looking at power electronics. And the point I'm trying to make here is it's not just the solar cell, but multiple types of solar cells, their applications, and going all the way to power electronics so that you have the full end-to-end application. So one of the first renewable-based DC microgrids is a full end-to-end technology that is available at our sister lab in Siri. This is this lab in Pilani, Siri Pilani. So again, if you happen to be in Rajasthan, please go visit them. And they have deployed these at multiple villages in Rajasthan, a full DC microgrid system. This is our Bhavnagar lab. The director of Bhavnagar lab is here, CSIR-NCL, and they have developed technologies where you can capture the heat from solar, not just the PV but also the heat, and use it for a variety of purposes such as for purification of water and also mixed PV as well as thermal mode. And these again have been deployed in multiple villages in northeast as well as in the western part of India. More details when Kannan is here with you, can tell you more details about it. The National Aeronautic Lab in Bangalore has also been looking at improving the efficiencies of solar cells. This technology is already licensed. It's called the NAL-SUN next generation coatings on the solar panels that improve the efficiencies of the solar cells. Again, details are available on the posters outside. And finally, wind energy. NAL is very keen to do this because they have access to carbon fibers, and when you go to beyond 95 meters windmill blades, it's only with carbon fiber blades, carbon fiber composite technology that you can make these large size blades. So light weighting is very, very important for these very large windmill blades, and NAL not only making carbon fibers but also converting them into composites. Sections that go on the windmill blades is an active area of research at NAL today. Finally, the last vertical, which is coal gasification. India has huge reserves of coal. This is not an easy coal to work with because it has very high ash content. So you need different kinds of technologies to deal with high ash content coal. And this is a technology which is called pressurized fluidized bed reactors, which takes the high ash coal and gasifies the carbon from that coal, converts that into syngas, and that syngas is then converted into a whole host of materials. Dr. Kalaiselvi also mentioned a little bit about it. So this is a 1.5 tons per day pilot plant which is working in Simfer. If you happen to be in Dhanbad, this is a plant that is worth seeing. And they have a plant that is fully integrated, not just gasification of coal, but also converting them, the syngas into methanol. So it's an end-to-end technology for converting coal into liquid fuels. And finally, at NCL, we take that methanol and we make dimethyl ether out of it. This is an important fuel because it is a full LPG substituent and a full diesel substituent. The idea is to convert methanol. We are agnostic to where methanol comes from. It can come from coal gasification, it can come from biomass gasification. We have a wonderful catalyst that converts the methanol to more than 99% conversion and 99% selectivity, converts into dimethyl ether, which goes as either LPG or diesel substituent. So a lot of these details are available in the exhibition outside. I invite all of you to please go and attend, see them, talk to the people and get to know more about us. Finally, I just want to say please connect with CSIR for co-developing our technologies to the next scale, and let us together help commercialize these fully indigenous technologies. Thank you very much for your attention. And
बहुत बहुत धन्यवाद सर। आपने इस राष्ट्रव्यापी कार्यक्रम की रूपरेखा बहुत ही कुशलता से प्रस्तुत की। बहुत बहुत आभार, बहुत बहुत धन्यवाद। तत्पश्चात बारी है आज के कार्यक्रम के प्रमुख अतिथि माननीय डॉक्टर सूर्या मोगंती जी को सुनने की, किंतु उसके पूर्व मैं आपको संक्षिप्त परिचय उनका प्रदान करना चाहूँगी, क्योंकि परिचय ही संबंधों की पहली सीढ़ी होती है। तो आइए इस प्रभावशाली शख्सियत से आपको रूबरू कराते हैं। डॉक्टर सूर्या मोगंती जी लॉर्सन एंड ट्यूब्रो ग्रीन टेक लिमिटेड के टेक्नोलॉजी हेड के प्रतिष्ठित पद पर कार्यरत हैं। इससे पूर्व उन्होंने लगभग 20 वर्षों तक न्यूयॉर्क की प्रतिष्ठित सियोनिक एनर्जी में चीफ टेक्नोलॉजी ऑफिसर के रूप में महत्वपूर्ण कार्य अनुभव प्राप्त किया है। उनकी शैक्षणिक यात्रा की बात करें तो उन्होंने केमिकल इंजीनियरिंग में कॉर्नेल यूनिवर्सिटी से पोस्ट डॉक्टरेट, क्लार्कसन यूनिवर्सिटी से पीएचडी और आईआईटी मद्रास से मास्टर डिग्री प्राप्त की है और जवाहरलाल नेहरू टेक्नोलॉजिकल यूनिवर्सिटी से बैचलर डिग्री उन्होंने प्राप्त की है। इसके अलावा उनके 20 से भी अधिक साइंटिफिक पब्लिकेशन हैं और उन्होंने विश्व स्तर पर लगभग 150 से अधिक पेटेंट के विकास में अपना महत्वपूर्ण योगदान दिया है। तो आइए इस महत्वपूर्ण शख्सियत, प्रभावशाली शख्सियत, इनके सम्मान में तालियां बजाएं। और मैं आपके सम्मान में कहना चाहूँगी कि मेहनत और हुनर किसी किसी को मिलता है, मेहनत और हुनर किसी किसी को मिलता है, ताली में असर किसी किसी में दिखता है। आप चलते हैं तो कारवां चल पड़ता है, आप चलते हैं तो कारवां चल पड़ता है। रहनुमाई का हुनर किसी किसी को मिलता है। जोरदार तालियों के बीच सादर आमंत्रित है डॉक्टर सूर्या मोहन को।
Thank you very much. My Hindi is not that great, so I cannot explain in Hindi, but dhanyawad. Well, I would like to again thank Dr. Ashish Lele for giving me this opportunity and the invitation. It's my privilege to be here, definitely. So what I would be doing is, unfortunately, I cannot talk about what Lasman Tubro is doing, what I'm doing. What I've done is I've made slides to talk about two general aspects. One is the critical minerals that are needed for energy transition. This is coming from IEA, International Energy Agency's report. Then I am free to talk about some of the work that I've done in my previous tenure. So I'm going to talk about a little bit on batteries. So I've constructed this presentation into two parts. One is to look at, as I said, the critical minerals. Hopefully I'll inspire the scientists here to start working on the next generation technologies that will overcome some of the challenges, as you can see. And then, second one is, being a scientist, I do want to showcase some of the original research that we have conducted in the past 10 years. Okay. So with that, let me start here. There is one. Got it. Thank you. This is a nice graph that I picked up from one of the sources here, where it kind of talks about how the cost of energy is changed over the last 140 plus years. So you can predominantly see the commodities like coal, oil-based energies have pretty much stagnant. There is no cost change ever since they were being used. However, the new technologies like we are working on, solar, wind and batteries, have experienced a nice decline in the cost, because at the end of the day, dollars, rupees, whatever you call it, cost is king. Any new technology that has to see the light, it needs to be affordable and it needs to be in a low cost. Otherwise, it doesn't matter how good that is, it will never come to life, because that's the unfortunate side of doing business. So where this kind of talks about a very nice story. One is, because of that, what happens is, you can see there is increased installations or users of these technologies, especially wind, solar and batteries. And hydrogen is coming, yet to come. It's not commercial yet, but whereas you can see these next generation technologies like Moore's law, you're familiar with, where in semiconductors every 2 years you're doubling the number of transistors, right? Likewise, we'll also perhaps will go into stage where every 2 years we will be doubling or maybe tripling the solar and wind generations, and as well as battery storage. All these technologies come with another side, that is the minerals or materials we call, right? So for example, electrification, copper and aluminum is pretty much needed across the board, whether it's solar to batteries, whichever technology that you take, copper and aluminum must have. These dark circles are high, and I can see moderate and then low. And whereas if you take about the EV batteries, you see there are a lot of other minerals that would require. It's either wind or an electric vehicle motors, they would require rare earth materials. Without that, the magnets won't work, right? So you need them. Likewise, of course, for lithium batteries, you need lithium. And then for most of the hydrogen related activities, PGM, platinum group metals, and the nickel play a dominant role. So why I'm bringing this up, because this is like a new oil in a way. I'll tell you that in a minute. So for example, these are nice bullet points. As I said, it's coming from this report. If the electric car uses 6 times more minerals than a conventional vehicle, ICE based, then wind farm requires more minerals than coal fired. So we are thinking of, okay, we are changing these technologies, but at the end of the day, you need to start thinking about where the materials are going to come, and who is producing those materials, and how do we tackle that? Because we know India as a country do not have a lot of minerals except for coal and maybe carbon, graphite for batteries. The rest of the things have to be imported again, like natural gas and coal and oil. So this is how, for example, a car battery looks like, where, as I said, this is an EV battery, EV-based vehicle, electric vehicle, requires a lot of graphite, copper for the windings, right? Then you have nickel, manganese, cobalt, and lithium that's coming from the battery. Whereas the gasoline-powered vehicle only requires copper and a little bit of manganese. So it was interesting where the manganese is used, but I was not able to find it. If somebody knows, do let me know. I'll try to understand where are we using manganese in IECs. But nevertheless, the rare earths, zinc, and other chemicals, minerals are heavily used in EVs. So likewise, there are other technologies. You can see, as I was just talking about, copper is predominant. Whether it's coal, natural gas, or any other technology, you have to use copper for transporting electrons, right? Likewise, solar uses a little bit of copper. Mostly, you have silicon, which is not a problem actually. Silicon is available, but again, making it and doing it at scale is also important for a country like us to become energy independent. So when it comes to now the hydrogen, probably the next big thing, there are certain type of minerals that are again used. Most of you know, depends on the technology type. So alkaline electrolyzers, one of the most matured ones, depends on mostly on the nickel. Then if you look at the next generation PEM, they uses platinum-based group materials. Then of course SOFC, again there are other type of rare earth materials are needed. So without that, doesn't matter what we do, it doesn't work, because these are pretty much heart of the technology, right? And then of course fuel cells would require platinum as well. So this is where the materials are coming from. So the top one is oil and natural gas. You can see pretty much US, Saudi Arabia, and Russia are dominating. But when it comes to the next gen technologies, they are geopolitically, I would say, concentrated. There are many places you are getting these from, not just one country where you have to be friends with. You have to be friends with many countries to get these materials. Likewise, that is where the mines are, and then you need to process them to get. So the idea is that where it is happening, there is no surprise. China has been dominating in terms of processing these minerals. So why am I putting up these slides is to give you guys some sense of where, when you have to go to industrialization, these are places where the materials are coming. And then my hope at the end is to convince the scientists sitting in this room is to work on materials that are readily available, develop technologies based on materials rather than the technology itself, how good that is compared on a paper. So then, what happens in the next 2 decades from now is there are multiple scenarios that people talk about in these reports. In order to hit the net zero, there is perhaps 6 times more need of them. The more and more you use these technologies, it's like natural gas or oil. You need the minerals to support the technological revolution at industrial scale. So there is a lot of these minerals that we would be needing. Either it's lithium, mostly for EV related, or nickel and rare earths for wind and EVs, and again for hydrogen, pretty much nickel is a important mineral to be looked at. But on the flip side, this kind of gives us another opportunity. So if you start using these technologies at scale, then you have a lot of these batteries or electrolyzers or fuel cells or solar or wind, other things, where you can start recycling, because I think that Ashish was talking about type 4 material, right, where you can reuse. That's where the thinking should be. Maybe unlike oil and gas, you import and you burn it off and convert it to CO2, these are not going to go away. They will be here. So we can start thinking about how do we recycle so that it becomes a circular economy where you bring them and they stay with you. So with that, what I would like to provide in my own opinion is there are certain type of innovations that needs to happen, and they should be focused on the material, the elements or the minerals that require, right? So idea is, okay, start thinking about using silicon instead of graphite, where if you can start adapting quicker, because the silicon is abundant, but using silicon in an anode, people working in the batteries know that it's not that easy. So you have to, there has to be innovation, technological innovation has to happen to make it a viable anode material. Likewise, so sulfur is another cathode. Of course, it's a low voltage, a little bit lower voltage compared to the known NMCs of the world in the batteries, but it's a byproduct in refineries. So if you can enable sulfur-based chemistries, that again becomes much more sustainable for energy storage applications. But however, of course, there are some challenges that need to be overcome. Likewise, if you start thinking about next generation, this sodium ion, and there's another angle. So again, start thinking about the cathode materials that would not require nickel and manganese, but if you start working on cathode materials that would require ions, said that this is what the PBA type of Persian blue analogs, that's another way to overcome the supply chain related challenges. And in the fuel cells and electrolyzers, of course, platinum is better for acidic conditions, but if we can develop again catalysts that are based on low cost material like nickel and iron, which can work at higher current densities, even though alkaline technology is mature, but there is a lot of innovation that can happen because it works at a lower current density. So if you can make it at a higher current density, then the footprint can be like what I'm envisioning here is a PAM-like footprint for alkaline. If you can do it with low cost, nickel-based, iron-based catalyst, then that can be definitely be a game-changing technology for us to have. Then I talked about this a little bit, where working on, which probably my humble request to CSIR labs is to start thinking about recycling activities. The technology is developed elsewhere, but you can start thinking about it. That may be useful down the line, not right now, perhaps maybe 1 or 2 decades from now. There will be a need, because we are one of the growing countries, the world economy. We will soon become consumers like the Western countries, where we will be importing technologies to use. Hence, we will have the ability to recycle and reuse these critical minerals that are needed for next generation energy needs. Okay, so that's the first part. Hopefully, I've kind of given you information that most of you might know, but I just want to put a perspective on that where this is going, because the minerals are critical for energy transition. Now I'll change gears and put some scientist hat on me and then talk about how do you solve a thermal runaway related activities for the batteries, because as we start thinking about electrification of many things, the safety becomes an issue, especially for the country like us, where the average temperatures are really high, and then you park the car or any other device that has a battery in it, then it will experience high thermal runaway events. There are many incidents that already happened. So this plays, hopefully. So this is a 40 amp hour power cell that we've done some nail penetration test. This is no longer a standard test anymore, because it is so violent. Almost all batteries fail this test. What is happening is it's fully charged, it's the size of a laptop cell, and then it's used in one of the electric cars. You put a nail, it short circuits immediately, the cell goes into thermal runaway. Then you know how do you study that? Being a scientist, it's very difficult, right? But there are multiple reactions that are happening. There is SCI decomposition, there is electrolytes that is volatile, and there is cathode that has oxygen in it. All these things actually happens in a way that they feed on each other. So end result is just fire. And in order to study that, there are beautiful techniques that we can use. One is accelerated rate calorimetry. And then, on a material level, you can use a differential scanning calorimetry. These two are techniques that will help you to understand what is happening on a cell level, what is happening at the material level. Because in a battery, the interfaces play a major role. So how the reaction happens between cathode and electrolyte interface and anode and electrolyte interface is critical for overcoming such kind of violent reactions. So these are how the typical plots would look like, where you are heating and then measuring the self-heating rate. It's a calorimeter, right, where you are measuring the self-heating rate of the cell. Based on that, you can understand what these reactions are, how are they propagating. And then on a DSE, on a material level, you can see basically the exotherm peaks will tell you where the reaction is happening on the cathode and electrolyte interface. Depending on these two, you can understand how stable the cell is and how to mitigate it. Because the mitigation happens on a pack level, as you see. What I'm trying to understand is inside the cell, how can you delay these so that the pack construction can be easier, so you don't have to over design, because at the end the cost of that comes as a penalty. Over designing the pack also comes as a penalty of the energy density, which translates to driving range and etc. But if you think about it, in the batteries, except electrolyte, there has been a lot of progress. On the cathode side, tremendous progress. On the anode side, okay, this graphite and now the silicon materials are being used. But the electrolyte has been stagnant, pretty much, at least in my view, ever since Sony has commercialized. It's a cocktail, lack of a better word. It has solvents, salt, and additives. And there are a lot of additives that were developed over past years to like a band-aid approach, where okay, I'm not getting life, so let me add this additive. I'm getting a gassing issue, let me add another additive. So there hasn't been any thought process put in industry at least to overcome these challenges from a fundamental understanding. So on the other hand, this electrolyte also, because it's carbonates, it's like a fuel, and then your cathode has oxygen. So whenever you have these kind of thermal runaway reactions, it's a closed system, and then it will feed on each other, because as soon as the degradation reactions are happening, you are producing oxygen from the cathode, and then you have a volatile electrolyte that catches fire. But there are other type of flame retardants and molecular firefighters, we call them phosphorus-based chemistries, that are known. People have been using, in electronics and furniture. You add phosphates that will prevent fires. So then the question is, why can't we use phosphorus compounds? Try to limit this, the thermal runaway reactions. The answer is no, because one of the great electrolyte scientists in batteries, Jeff Don from Dalhousie University back in 2012, has used the phosphorus, one of the well-known phosphate, the triphenyl phosphate in the battery, and found that adding this particular compound to battery makes it, instead of making it less safe, it makes it more reactive. The reason is these phosphate molecules are reactive with the highly charged oxides also on the graphite side. So then, if you can overcome this oxidative stability, perhaps you can find a way. That's where we have done some work where you can, it's again a basic chemistry. So if you can take fluorine and other type of elements and then change the molecular structure, we call it molecular engineering. So can you make changes which is done in, for example, in pharmaceuticals and others, where they design molecules to attack a particular drug. Similar kind of mindset can be applied here. So you can engineer the phosphate molecule to do that. In order to do that, what we have done is, we've used the multiple types of functionalities that you can put. but you can take help of density functional theory to know what is the homo-lumo values. Using that, you can down select some of the functional groups. That's what we've done, where use DFT to really understand which compound, which additive, which functional group we should put on, and then sure we found that some of the phosphates with the changing the functionality, you can make them a little more oxidatively stable. Then you can utilize the phosphorus function in the battery, right? So nevertheless, we have done some of the DSC. Again, I was talking about differential scanning calorimetry on the cathode, and you can see whether are you shifting these reactions to higher temperatures. Is the energy that's released is less or not? Sure, by adding 10% of these engineered phosphates, you can do that to a degree. But then, how do you come up with electrolyte? As I said, electrolyte is a cocktail. It's, you just buy the electrolyte from electrolyte suppliers and then use it. But if you want to design, it's a Herculean task. It's not that easy, because you have solvents to choose from, you have salts to choose from, and you have additives to choose from, and then at the end you have this new phosphate that you want to choose. So how do you do this in a faster way, right? Thankfully, there are some statistical tools that one can use. One of them is Taguchi methodology. Highly encourage people to use, because when you combine these to your basic R&D, you can compress the timelines, because when you work in industry, you need the results yesterday, right? So there is no tomorrow, day after. You need it yesterday. That means that you need to fast forward everything. So using statistics is one of the greatest tool to minimize number of experiments. So what we have done here is we've taken 8 different control factors. Then if you were to do a traditional, lack of a better word, Edisonian approach, then you would be doing 4,374 experiments. But with Taguchi analysis, you can limit those to only 80. So from there, you can understand how the interactions are played between different compounds, and then hopefully come up with a product, in this case, a new electrolyte composition. Nevertheless, we have done that. These are all cells, 5 amp hour cells, at least 3 to 5 cells per group, and then you can see the capacity is pretty much matching, and then you started cycling at a little bit faster rate, and these are 2000 cycles, give or take. It takes 5 months to get even at 1C charge discharge. So it's okay, 5 months, but still you can get a very good valuable data. From there you can start thinking about which electrolyte is going to be looking good, right? Then you do these arc measurements to see is there any improvement in the self-heating rates. And I will not go to the, some of you probably are experts in this better than I do. So you can understand which one is playing a role that you wanted, meaning in this case lowering the self-heating rate and making it a better electrolyte. Then we also did more practical, which is hot box. You throw the cell into an oven, increase the temperature to 170, because at 130 the separator started to melt, right? Then some of the electrolytes sure pass the test. They also have the performance, they also pass the thermal stability. So then finally you can start thinking about making a champion electrolyte which shows both performance. This is a reference which fails, and then you have an electrolyte composition that passes for this particular. Then like that you can start. The idea behind showing these is there's always a way, and there is always a way to solve problems, but if you use the right tools and the right mindset with the right direction. So that was my intent of showing. Of course, you're all well accomplished scientists. You will do very good in your own way, but try to understand this bigger picture of where your technology will go, and if you have developed something, and always think about mass adoption, right? Why industry would take it? Because it has to be cheaper, better, faster. So with that, there are other ways to do this, but I think I've taken a little longer than what I was given at the allotted time. So let me pause and thank you for listening. And I'm open for any questions.
So, Surya, the mining, we have a team one of the important programs in that theme is recycling of batteries, and full recycling, not just the black mass, but extracting all the metals from it. Right? And 3-4 labs have been involved. CSMCRI was involved, NML is involved, IMMT is involved. So the multiple labs working on this, and there is a pilot plant also set up, and I think 2 or 3 licensing also has been done. So there's an active program going on in that.
Sorry,
No, it's
ignorant on
great.
that,
It's
but
very relevant, but we're just saying that there is some work happening in CSIR on that.
good to hear that, because that's, as I said, it's one of the critical things that we should do.
So there was one graph which you showed in the beginning where the cost of units generated from coal and other technologies are compared, and coal was remaining relatively stable over a long period of time, whereas I think batteries, solar and wind, the cost was coming down. So any explanations as to why that is applicable only to certain technologies and for certain it remains flat?
The reason is, initially when you start a new technology, it's a good question by the way, there always will be initial inertia of adaptation. They will be expensive, right? But there are policies that are helping, for example, IRA and other things in the world that are helping batteries to come down with the cost. And also the other reason I think is because of awareness. People are forced to start thinking about adapting green energy technologies. So those are 2 things. One is policy, there is awareness, and the technology advancements that are helping to come down the cost. Because when they started, it's actually a logarithmic graph, right? So very high. Now they are coming down, and they are enjoying the cost benefit because of these things. Hopefully I answered.
A lot of battery enthusiasts sitting in the audience. No questions?
Take it offline.
Okay, all right.
Hello, sir. Nice presentation. Just a curious question: whether you look for the like electronic waste management. As sir has said, we have some wings which are working, because electric vehicles and with the time, with the advent in the technology, there will be the piles of batteries everywhere. So are you also into recycling like everything, and policy management in terms of this?
Yeah, good question. I don't think I can comment on that from L&T perspective, because we don't have any plans as of now.
Okay.
But I think that should be a very good business model to get in. There are a couple of startups I heard that they are doing it. As I was saying, right, so with our growing economy, we would definitely be using more and more of these next generation technologies. So it will be a very good business model for people to start thinking about. At the end, of course, economics plays a major role. If you have the right technology and if we can do it at a cost, then definitely yes.
Thank you, sir, for highlighting the darker side of the green energy. As you rightly said, their availability of those minerals along with the coal is limited. In that scenario, how the industry foresee the future of energy, whether it is limiting up to their availability, or we are looking into some different kind of energy which is viable or which will be sustainable for a longer period?
Good question. There is no simple answer to that. That's typically, at the end of the day, cost is the main driver. So if you can put up a technology and then start selling it at a profit, definitely industry will look at it. That's one of the reasons probably alkaline electrolyzers, as an example, is taking off, because you don't have a lot of minerals, only nickel to deal with, and that's not an issue because we use nickel in other steel and other areas as well. Then if you think about batteries, you see press releases, a lot of iron based batteries are LFP, right, rather than the nickel, manganese, cobalt, NMC type of coming, because it's sustainable, cheaper cathode to begin with. So you have to start adapting the technologies because there is a need. Then you adapt the technologies that have less supply chain risk.
Thank you.
I think we can ask one more and then we should end, because we have a next session coming up.
Very nice presentation. I just wanted to know this solid-state batteries, SSP's plan for L&T perspective, because we have now started the SSP as one of the prime activities in our battery sectors, the CSIR. So what is your plan for this, especially for the LLZO, lanthanum lithium zirconate systems and thereof?
So one, it has to be cost competitive. I don't think it is yet. That's just my view. Second, of course, the supply chain again, right? So solid state for mass adaptation, is my personal view, is little far compared to other technologies that are currently available. So the lithium ion, even we don't have a gigafactory of lithium ion yet in the country. So we'll be still importing them. So if you were to look at it, I think it would be LFP, NMC, and at the end, the solid state. Okay, thank you.
धन्यवाद डॉक्टर सूर्या जी, आपने अत्यंत ही प्रभावशाली तरीके से हम सभी का ज्ञानवर्धन किया और बहुत ही महत्वपूर्ण तकनीकी जानकारियाँ उपलब्ध कराई। निश्चित रूप से यहाँ पर उपस्थित प्रत्येक व्यक्ति लाभान्वित हुआ होगा। जोरदार तालियों से उनका आभार करें। कैन वी हैव लाउडर अप्लॉज? ये हुई ना बात। अब मैं हमारे मुख्य अतिथि आदरणीय डॉक्टर सर से निवेदन करूंगी कि वे एग्जीबिशन का विधिवत उद्घाटन करें।
लाइट ऑफ कर, आनंद लाइट ऑफ।
लाइट
Go ahead. Said only once.
उद्घाटन की सभी को बहुत बहुत बधाइयाँ। और इसके पश्चात मैं कुछ महत्वपूर्ण सूचनाएं आप सभी को देना चाहूँगी कि लंच के पश्चात टेक्निकल सेशन इसी हॉल में होगा और 4:30 बजे प्रेस मीट आयोजित की गई है। तो मैं निवेदन करना चाहूँगी सभी सम्मानीय CSIR डायरेक्टर्स और उनके रिप्रेजेंटेटिव से कि वे यहाँ 4:30 बजे उपस्थित रहें। और पानी और वॉशरूम की व्यवस्था इस हॉल के बाहर राइट साइड में की गई है, कृपया ध्यान दीजिएगा। और इसके साथ हम बढ़ते हैं कार्यक्रम के अगले चरण में। मैं निवेदन करना चाहूँगी सभी सम्मानीय CSIR डायरेक्टर्स से कि वे कृपया मंच पे या उनके रिप्रेजेंटेटिव्स भी कृपया मंच पर आएँ कुछ क्षणों के लिए।
बैठना नहीं, अभी खड़े
ग्रुप फोटो। थोड़ा बहुत
आनंद
नाही podium खूप जड आहे खूप जड आहे खूप जड आहे.
सर थोड़ा सा ऊपर पकड़ो. हाँ यस.
Thank you. We have to have a social media post, right?
There's a post event.
होतं ना का नाही आलं ना आता कॅमेरा ह्याच्यावर टाक हां स्टॉल
There is one more announcement. Those who have registered online, they have not collected their registration kits. Please collect. There's a registration stall just opposite.